Yo, what is up, guys? Welcome back. Episode 141. Believe it or not, I was literally recording the first half of this video, maybe the first 25 minutes, and my power cut out. It's been kind of like stormy, rainy outside today, so, um, yeah, I literally was doing a problem. Well, I finished the problem, and we jumped into the next one, and completely cut. We actually were looking at graph problem over here. Problem that we had solved before, number of islands. Submitted it 7 minutes ago. Everything cut out. So, I mean, it's whatever. We're gonna jump into another problem. We'll do our Pokemon sound of the day again. I can't recover the footage, so I guess we'll do it again. We have Kubu Tops today. Kubu Tops Pokemon sound. Take a look at the sound again. I'll happily mimic it again.
Take what you
There's that sound. You know, Koopa Top sound. I've never even used Pokemon before, but interesting. But yeah. Jump into another problem. We were doing actually a hard problem. We actually were just beginning to look at it. Check out the study plan. Go back. We did this one here, just one that we already done. We're gonna check out critical connections in a network. This problem here we were discussing, pretty much this problem here is that this problem is telling you is a critical connection is a connection that if removed will make servers unable to reach some other server. So I assume here that every single graph that you're given is connected to each node. And if you remove one of the nodes and there's two separate components, then that's a critical connection. So in this case here, the critical connections would be this one. And that's really it, right? Because if you get rid of this one, you can still get there, right? So from what we know is that, well, I don't know if this is a shortcut now that I think about it, but we're going to know that this node is a critical connection if we only have one outgoing edge. So could that be a little trick here to this problem? I don't know. There are no repeated connections. Because technically, right, if we have more than two connections, then we have more than two ways to get to that node, right? Use Tajin's algorithm. What the hell is this? A directly connected graph is a strong path. Connected component. Oh my gosh, dude. Two DFS traversals of the graph. Produce a DFS tree. Damn, I was really just thinking, well, if there's one outgoing edge, then it has to be critical edge, right? Because in this case here, the critical edges are two here, this one and this one. Well, actually, are they directed? They're undirected edges. I'm going to take a look on the, if I'm thinking of this question correctly. 192 critical connections in a network. The true nature. Okay. Yeah, because you're right. Yeah, it could be. We could have this one and this one over here, right? Or we have two edges. Tajin's algorithm for bridges. Key idea is to use DFS and keep track of discovery time, lowest reachable time. Why single edges aren't enough? Man, Tajin's algorithm, man. What? Graph DFS. Is there a Leetcode video on this, maybe? Let's take a look. Oh, whoops. What am I doing? Leetcode doesn't have a video on this one. Wow. I really would have thought he would. Let's take a look at TechDose's video.
Empower your students to be more authentic, impactful.
Okay.
And in this video, we will see the critical connections in a network problem, which is from Leetcode number 1192, and this problem can be solved by using the Tarjan's algorithm for bridges. Now, let us first read the problem statement. In this problem, there are n servers numbered from 0 to n-1 connected by undirected server-to-server connections, forming a network where connection set I is the connection between node A and node B, which represents a connection between servers A and B, and any server can reach any other server directly or indirectly through a network. A critical connection is a connection that, if removed, will make some server unable to reach some other server. We have to return all the critical connections present in our network in any order. Okay, so let us see an example in order to understand. Let us assume that this is our given graph. Now in this given graph, if we assume that these nodes are basically our servers and these red lines, that is the edges, are nothing but our connections, then which connections can we remove in order to separate the servers? That means, let us say if we remove this connection from 1 to 2, then are these servers 1 and 2 separated? You can see that it is not separated. There will be a path from 1 to 3 and again from 3 to 2, so they will not be separated. So in this case, critical connections are nothing but bridges. And what is a bridge? An edge is a bridge, removing which increases the number of components in a graph. So if you remove a connection and that is increasing the number of components in the graph, then that will be a bridge and that will also be a critical connection. In this case, this edge 1, 2 is not a critical connection. If you try to remove this edge 1, 4, then you can see that you cannot reach from 1 to 4 because this was the only connection using which you were able to reach it. So this edge 1, 4 will be a critical connection. Now if you look at this edge 4, 5, then this is also a critical connection because this will be creating two different components. So whenever if you remove an edge and it is creating two different components, then that connection will be a critical connection. In this case, we are having three critical connections from 1 to 4, 4 to 5 and 2 to 6. So these three edges are basically our critical connections. No other edge is a critical connection. Now in this case, you cannot remove multiple edges and say that they are critical connections. You are only allowed to remove only one edge at a time. Okay. And if you want to remove some other edge, then the already removed edge must be put in its place. So at a time, you can remove only one edge. So this is the definition of a bridge. So this problem can be reduced to finding all the bridges present in the graph. So I have already shown in my another video how to find all the bridges in a given graph using Tarjan's algorithm. So the link for that video will be present in the description below. You can check that out. That video is having...
Man, that was probably the worst explanation of a problem. I think he just literally spoke about what a critical edge is. Like, that was like... Recently had an Amazon coding round past 2 days. It's the same question I got there.
The full explanation about this problem, you can simply apply the same logic and the code and that will work. The only thing you need to do in order to solve this problem is first form the adjacency list, and after forming it you need to just apply the Tarjan's algorithm. So I hope you remember the Tarjan's algorithm. If you don't, then please look at my video. The link will be in the description below.
Like, I feel like there was no explanation there. Let's just start off by doing the adjacency list, right? Passing edges, right? We'll create our graph here. For I in, we have 0, 1, 2, 3. What does this represent? We have an edge from 1 to 3. Okay. right? Because, hang on. At node 0, we have an edge to node 1. And vice versa, right? So we can do, well, for our edge in edges, AB is equal to edge. If graph A not in, let's see, if A not in graph A is equal to this. If B not in graph B is equal to this. Otherwise, we can do graph A dot append B, graph B dot append A, right? And we would just simply just return our graph. Okay, let's call our adjacency list here, make it equal to adjacency list graph. We can print our graph. See what that gives us. This is connections here. Okay, that looks good. So now we have to figure out what Tarjan's algorithm really is. The time a vertex is first visited during the DFS traversal, a low link value, the smallest discovery time of any vertex stack used to track vertices. Node 0 was first visited. So we return the edges in a list of a list. Okay, so obviously we're gonna need some sort of res array, right? Okay. Given a connected undirected graph, find all critical connections. Okay, so this is Tarjan's algorithm. We use DFS along with disk U, time when U is first discovered in DFS. Low U, the lowest discovery time reachable from U through its subtree or via a back edge. If you visit a neighbor V of U and find that low V is greater than disk U, it means V can't reach U or any ancestor of U without using the edge UV. So UV is a bridge, critical connection. Intuition with an example. Let's say you have a graph. Critical connection. Step 1, build the graph. Okay, step 2, initialize the arrays. We initialize with discovery times, lowest times, mutable counter, shed, and recursion. Okay, so we created a res. Okay. Created a graph. The disk is equal to -1 times n. We use -1 to show that it's not discovered yet. So low is equal to -1 times n. And then we have a time, which is apparently shared across multiple things, right? So here we have our DFS. So we have our node and our parent, right? Okay, we want to call start DFS from node 0. Right, so we go DFS 0, and the parent is -1, right? Because we don't know. Right? We would return res. This is what we're gonna return, right? We're gonna add each critical edge into res here, right? Okay, so right, we have a forgot to do def. Okay. So we start off in here and we start off disk U discovery current node that we're at is equal to low U is equal to time 0. So disk node is equal to low node is equal to time 0. Time 0 plus or equal to 1. What is time useful here? I'm confused what time is used for. In the algorithm, time is used to assign discovery times to each node when they are first visited during the event. That's how it works. Node U is first visited. Gets a unique timestamp. It's interesting. Uniquely identify the order in which nodes are visited. It is critical for calculating disk and low. Without it, you wouldn't know how early a node was reached in the DFS reversal, making it impossible to detect bridges. Okay. Alright, so we do this. And we go, okay, so for neighbor in graph node, if neighbor is equal to parent, we want to continue. Okay. If disk neighbor is equal to -1, okay, it's not discovered, right? So then we call our DFS function with our neighbor and then our node as a parent. Then we go, well, low node is equal to the min of low node, low neighbor. I don't know why we're doing this here though. If low neighbor is greater than disk node and res.append, then we know we found a connection here, right? Which would be node neighbor. Else low node is equal to min low node disk neighbor. Okay. To go through this code is quite difficult, right? So obviously this creates the adjacency list. We don't worry about this. We create the adjacency list here. We're setting it to -1 because this is kind of using our visited array, right? Or our visited set that we usually use in DFS. So there is definitely other ways to do this, right? we make disk node is equal to low node is equal to times 0. So we're making disk node is equal to low node, which is equal to times 0. We're making times 0 equal to both low node and disk node. Alright, so this is the time at which they were discovered. Right? And then we're increasing times 0 plus or equal to 1. Okay. For a neighboring graph, we loop through each neighbor, right? If the neighbor is equal to the parent, right? So if we're here and let's print our graph so we can visualize what we're looking at. We see we're looking at 1 right now, right? So it's going to go into here. It's equal to -1. DFS neighbor node. We're going to call that and we're going to do that, right? If it's not discovered. That's just what I don't understand here. We go low node is equal to the min of low node, low neighbor. So we're trying to get the minimum. Low node, low neighbor. So the minimum of these two. I think I need, can you explain this code? I understand this part, what it's doing. I just don't get why it's doing this. Right, this is what I'm confused about, this part here. I don't get, like... I don't get this part. First discovered, yeah, the timestamp when it was first discovered. The lowest discovery time reachable from this node or a subtree via tree edges or back edges. What are we doing here? We're deciding whether the edge between node and neighbor is a bridge. If removing it, it would disconnect the graph. Deeper in the DFS. If this neighbor is equal to -1, we're going deeper in the DFS. After recursion returns. This is so confusing. This is really, really confusing. It's kind of throwing me off a bit. Maybe we're gonna have to paint this. This is critical. We're just gonna label it. Okay. So time is a shade counter. This is our res rate. Our disk is when it's first discovered. Okay, our low is the lowest discovery time. If low neighbor we're checking for critical edge here, right? If low neighbor is greater than disk node, so if the lowest discovery time for this node is greater than and GPT's having a hard time explaining this to me because I'm not getting it. Critical edge if low. So we find the minimum here, right, of the lowest discovery time. Because we keep going through, we keep running the DFS, we keep returning back, and we find the min discovery time, right? So really it goes all the way through, right? Checks, well. Freaking GPT's like preparing an image for me, bro. Like, I can't even stop the image creation, dude. What is going on here? I don't think we're gonna get it, dude. I just don't get fundamentally tells if there's a way to reach an earlier node than this node. Try to update load. You have parts in the graph. Maybe I'm gonna ask it for the recursion stack because the recursion stack helps a lot. Okay, time. DFS 0 minus 1, right? So we're going 0. So this 0 is equal to time is equal to 1. Explore neighbors 0, 1, 2. So then we call 1, 0, right? So we're looking at this edge here, right? Neighbor of 0. We do this one is equal to low one is equal to 1. Time is equal to 2. Neighbors are 1, 0, and 3. Skip 0 since it's the parent, right? So we do this, right? We skip. Don't want to go back. This is what visitor does, right? So then we skip 0 because of the parent. We look at 3, 1 right here, right? Time is equal to 3. Neighbors of 3 is 1. Neighbors of 3 is 1. DFS 3, 1, neighbor of 1. 1, 2, 4, 5. Dude, I need to do it with this test case. I think we're getting the wrong test case. Zero, 1, 1, 0, 2, 1. Neighbors. Start at 0 minus 1. We go to 1, 0. Right? Time to neighbors. Bro, what is going on here, dude? I think they're getting the test cases wrong, dude. Like, zero, 1, 1, 0. Neighbors of 1 is 0, 2, and 3. Yes, that is correct. Skip 0, that's a parent. DFS 2, 1. So we're looking at this edge up here now, right? This 2 is equal to low 2 is equal to 2 times equal to 3. Neighbors of 2 is 1, 0. Skip neighbor 1 because it's the parent. Neighbor 0 discovered already. Back edge found. Right? So, right, it doesn't, it triggers here, right? So then we trigger the back edge and we go low 2 is equal to min. Low 2 disk 0. Min 2, 0 is equal to 0. Return from DFS 2, 1. Back to DFS 1, 0. Update low. Low 1, low 2 is equal to min 1, 0 is equal to 0. DFS 3, 1, neighbor of 1. I think we're going to have to come back to this. I'm going to give up on it. It's a little confusing. I think I got to watch a video or something and go an in-depth tutorial. We're going to do a simple problem. I just feel better about myself because we did attempt a hard problem, but the concept was too difficult. I just don't think I was understanding the, what is it? The arrays. Like I understood what we had to do, but I wasn't fully functioning what the disk array and the low array, like GPT was telling me what it was doing, but I didn't really fully understand like why. And I feel like I just got to get that click and I'll understand, but I just didn't really fully understand the algorithm. So come back to it another time. It was a hard problem though, so I don't feel totally bad about myself, but I mean, it just definitely does suck, but it's okay. Let's look for an easy problem just to feel better about ourselves. Couldn't complete the hard problem. It is what it is, but implement a queue using stacks. I don't know why. Ugh, this is a design one, dude. I hate the design ones. Let's just do it anyway. Implement a first in, first out FIFO queue using only 2 stacks. The implemented queue should support all functions: normal queue, push, peak, pop, and empty. Implement the myQueue class. Void push. Pushes an element X to the back of the queue. So we have to make a queue from a stack. That's so interesting. Self.stack is equal to this, right? If we want to push an element, pushes an element to the back of the queue. How do you do that, dude? Pushes an element to the back of the queue. You can only use using SU. Okay. So the trick is that we need to use 2 stacks. I wouldn't not have thought about that, dude. So we need an in stack and we need a self.out stack, right? Okay, we push every element, right? So if we want to push an element, self.inStack.append X, right? If we want to pop an element, right? Because pushes the X to the back of the queue, right? Removes the element from the front of the queue and returns it. So if we want to do this, we'd have to go... We'd have to reverse it, right? So... I think we have to do a for loop, right? While self.inStack, I feel like we gotta pop it. Self.inStack.pop, and then we do self.outStack.append append X. Here we'd have to return self.outStack.pop, right? Here we probably want to check though if in stack oh, is it if turn self.outStack.pop. Yeah, that's right. stack. Peak here returns the element at the front of the queue. We have to do the peak here. So we'd have to go to find the peak of the queue. Peak is the first element out. So I think we'd probably do the same thing. No? But instead this would be peak. Is there a peak in this? Oh yeah, maybe it would be -1. -1. Okay, empty would be returns true if the queue is empty. So well, I guess it would just be if there's nothing in. If it's empty, then it would be in stack and out stack would both be empty. If not self.out stack and not self.in stack, turn true, else return false. There we go. That was a trick. We used 2 stacks. I would have never thought about that if I didn't kind of get a little hint there, but I'm sure no, there's no hint. An internship interview of a company 2 years ago. This full or later is empty. This is not only a trick. Terrible problem. Let's submit it, see if it works. Okay, alright. Well, we attempted a hard problem today. Well, actually, we kind of looked at 3 problems today, but, you know, we did attempt that hard problem. So that was fun. Definitely probably need a little bit more practice with the hard problems. I feel like the hard problem is really just trying to make us implement, like, hard algorithms that, you know, I feel like is, you know, a lot different than just, like, a normal implementation or a BFS or a DFS or whatever it is. So, I appreciate you guys watching. I'll be streaming tomorrow, so probably 7 p.m. Central. Probably going to work on that stuff tonight. Probably have some dinner, work on that stuff, figure out how to get the OBS hooked up to the YouTube stream, and then we're going to stream tomorrow for the first time. Probably be a couple hour stream, something like that, so should be pretty fun. I appreciate you guys. Thank you for the support, and I will see you guys tomorrow.